Okay, unit 3, the induction motor design. Okay, in that first content we are going to discuss about the output equation of induction motor. Okay, while you are considering the any of output equation, you should consider the EMF equation of the induction machine. So the EMF equation, that is the turns per phase, EMF per phase, it should be equal to 4.44 into F into pi into T phase into kWs, whereas F is the frequency, phi is the flux, and turns per phase, and the winding factor kWs. Okay, so while we are finding the EM output equation, the kVA rating of the induction machine Q, it should be equal 3 phase. That is why you can multiply with 3 into EMF per phase into flow of current per phase into 10 power minus 3. So you can substitute the EMF equation in this expression, then you can simplify it. Then whereas the frequency, so frequency F, it should be equal to, we can find the frequency F from the synchronous speed expression, that is the ns, it should be equal to 120 F by P. So from that you can find the F, it should be equal to capital NS P divided by 120. So we are always considering the speed in the RPS, so you can NS speed in RPS, it should be equal to synchronous speed divided by 60. So from that F, it should be equal to NS P divided by 2. Why you are finding the F in terms of P? So we need to substitute the total electrical loading and total magnetic loading. Okay, so the NSP divided by 2, you are replacing the F and you are substituting it. And similarly, turns per phase, it should be, current per phase, it should be equal to actual flow of current in the phase. So I phase we can replace in terms of IZ, that you can replace it and you can substitute it, and you can find there is no Z term. While you are substituting the Z term, Z means that is the total number of conductor that was missing here. That is why they are given turns per phase. So you need to convert in terms of Z. So you can consider this equation. The total number of conductor, it should be equal number of phase into 2 into turns per phase. From that you can find it out, turns per phase, it should be equal to Z divided by 6. So just you can replace in turns per phase in terms of Z divided by 6, that you can substitute and you can eliminate it. Then similarly you can group the magnetic loading and the electric loading. So P pi, that is the total electrical magnetic loading, IZ and TZ, that is the electric loading. So you can consider both the expression. From that you can obtain P pi as well as IZ and TZ. That particular expression you can substitute in the previous Q equation. Then you can find the output equation. So while you are substituting the magnetic loading, BAV into pi into DL, similarly AC into pi into T, the remaining all it should be repeated again. So you can multiply, there is the both pi is there, pi square, similarly D square L, similarly BAV, AC, that all expression you can repeat again. Then Q, it should be equal to C naught into D square L NS, the C naught is the output coefficient. So you can, the remaining all term, that is the 1.11 into pi square, BAV, AC and winding factor, that you can put the expression, that is the winding coefficient, output coefficient. So then here this expression is in terms of kVA. While you are solving the problem, they may give the value in terms of horsepower as well as kilowatts. If they are given like that, you can use this formula to convert in terms of kilowatts. The Q, it should be equal to kW divided by efficiency into power factor. So once you are founded the Q value and you can find easily the remaining all, then you can modify this expression in terms of D square L. Then you finally you obtain the value of main dimension D and L by using this expression, that we will discuss in the next coming class. Okay, thank you.